Hello, this is question 4 from the 2019 MAT. In this question, we will consider subsets S of the xy plane and points A, B, which may or may not be in S. We'll be interested in those points of S which are nearest to the point A, B. Okay, there may be many such points, a unique such point, or no such point. Okay, that's an interesting idea. Part 1, let S be the disk x squared plus y squared is less than or equal to 1. For a given point A, B, find the unique point of S which is closest to A, B. You will need to consider separately the cases when a squared plus b squared is greater than 1 and when a squared plus b squared is less than or equal to 1. Right, well, that second option is going to be much easier, isn't it? They're saying we've got the setup is we've got this disk centered on the origin. We've got some point, any old point now that we're taking in the xy plane. So it could be outside the disk, it could be inside the disk. If we've got then that a squared plus b squared is less than or equal to 1, then we've got the AB is inside S, it's inside the disk. So this is what they were talking about at the start of the question then. Subsets S of the xy plane points AB which may or may not be in S. So this is when AB is in S. Then that means that our nearest point to AB is going to be AB. Nearest to AB in S is AB, because you've both got the point and the points inside of S. And in this case, they just happen to coincide. If we're outside, then we're going to want to take a line over at that point. We're going to have to point on the edge of the disk, aren't we? We're going to go from the origin over to our point AB and then take the point on the edge of the disk, because that's going to be the point which is nearest. So we've got x squared plus b squared. I keep saying x. A squared plus b squared is greater than 1. So we've got a line then which is going to be y equals, well, b over a is the gradient, isn't it? B over a x. And we've got that x squared plus y squared is equal to 1 because we want to get a point on the edge of the disk. So we want to have where those two things intersect. So that's going to give us, well, we got x squared 1 plus b squared over a squared equals 1. So we're getting that x is going to be equal to the square root of a squared over a squared plus b squared. So that's that bit. And then for y, we are going to have, what are we getting for y? We're multiplying our x squared by b squared over a squared. So we're going to get the square root. That's going to change to a b squared. A squared plus b squared at the bottom. Right. So that was okay. Part 2, describe without further justification, which is always nice, an example of a subset S and a point AB such that there is no point of S nearest to AB. Right, this is coming back to the thing that was baffling me a little bit in the question when I was reading it. So we need to have some point AB and we need to have some set S, whatever is going on somewhere else. The AB, well, AB can't be in S, otherwise we've got that AB is then the closest point to itself. So AB has got to be outside of S. But somehow, if we take all the points in S, whatever point we pick, there's always a point that's nearer, but we never get to AB. So actually expressing it that way makes it a lot clearer to see what's going on. So yeah, whatever point we pick in S, so there must be an infinite number of points in S because we can always get closer to AB, but we never get to AB. So we need to have one of these limits, you know, like the one I always like of the frog jumping to the wall. If you keep jumping, well, it isn't jumping halfway to the wall, but if you've got the wall, you jump halfway and then halfway again, you keep getting closer, but you never get there. So that's the sort of thing that we want. So if we had a fuzzy edged disk, so say we turn the disk that we had in the previous part of the question and we take out the equals bit in the inequality. So we'll have x squared plus y squared is less than 1. So we've got a disk with no defined edge. We can always get closer to 1. And then some point, how do I want us to express this? That's our subset S, and a point AB such that there is no point of S nearest to AB. So we just need to pick any point which is outside of the disk. So let's go for 10, 10. That's definitely outside of that fuzzy edged disk. Okay, yeah, talking that through made that a lot clearer. It sounded really odd at first reading. Part 3, describe, again without further justification, an example of a subset S and a point AB such that there is more than one point of S nearest to AB. Right, that is a lot easier to do because now we can take a circle with a center of a circle. That's just the classic way of getting. You could have anything where you've got a point at some kind of focus with a symmetrical pattern around it. But let's go with that then. So we'll have our circle x squared plus y squared is equal to 1, and then we'll take the origin, and then all of those points on the circle are 1 away from the origin. That was good. Right, now part 4, let S denote the line with equation y equals mx plus c. Obtain an expression for the distance of AB from a general point of S. Then show that there's a unique point of S nearest to AB. Right, they just want us to do distance between 2 points, which is strangely straightforward. So the distance is going to be the square root of the change in x squared plus the change in y squared. This is going back to when we were 14 or something doing this. So that's the square root of x minus a squared plus mx plus c minus b squared. Square root a whole lot. So that's our distance then, and now we have to show that there is a unique point of S nearest to AB. So we're just differentiating this then. So if this is our distance, so let's say that the distance, if we've got y is equal to square root of x minus a squared plus mx plus c minus b squared, because we can see that although on the face of it this might be looking like a complicated equation to differentiate, it's not really, because we're going to get that half is then going to go to a minus a half when we differentiate it. So y is going to end up on the denominator. We're going to end up getting, well, actually the half is going to cancel with those 2's. So we'll have x minus a plus m times mx plus c minus b, and then all of that divided by y has got to be equal to 0. So we got that x minus a plus m squared x plus mc minus mb is equal to 0, which has one solution for x. One solution for x. We've got a linear equation in x that we're only going to get one place that is actually going to cut the axis. So that's showing that we've got a unique point. Okay, right, well, let's fill up that sheet. Let's get a new sheet up for the last 2 parts. Part 5. For some subset S and for any point AB, the nearest point of S to AB is that. Describe the subset S. Right, okay, so we've got, well, these points, so the nearest point of S to AB. So these are all points in S. That's a description of points in S. So we've got the X is, because you can see the way I'm going, just to give a bit of heads up on this in advance then, is you can see all of these S's we're defining as relationships between y and x. So we've got y equals mx plus c, x squared plus y squared is less than or equal to 1. So we want to get a relationship between x, which is a plus 2b minus 2 over 5, and y, which is 2a plus 4b plus 1 over 5. Well, we can see these things are pretty similar already. I mean, they've just doubled up x here. So what happens if we do 2x? So 2x is 2a plus 4b minus 4 over 5. So that is equal to y plus how many? We've got minus 4/5 up to 1/5. So we've got y plus 1 on that, haven't we? Y minus 1 on that. Yes. So that is equal to y minus 1. As we've gone from 1/5 down to 4/5. So we've got then that y is equal to 2x plus 1. Okay, so yeah, thinking about all the AB stuff is a little bit of a red herring in all of that. This is just the definition of the points in S. We're describing what S is. So just getting that relationship between those works out fine. All right, last part of the question then. Say now that S has the property that for any 2 points P and Q in S, the line segment PQ is also in S. Right, okay, so we've got 2 points P and Q in S, join them up, all those points are in S as well. Right, show that for a given point AB, there cannot be 2 distinct points of S which are nearest to AB. Right, this is just pulling together all the stuff we've just done. So we've got a whole load of things we can say with this then. If AB is in S, then AB is nearest point. So that is just 1 point, i.e. 1 point. Then if it's not in S, then where can we put AB? It's either going to be if AB is not in S, then we've got one of P is nearest, Q is nearest, or a point on the line, some point on PQ is nearest, and that was what we showed in the earlier part of the question in part 4. So this is then 1 point, 1 point, and 1 point as per part 4. So yeah, whatever we end up doing, we're getting exactly the same outcome of having one nearest point. You know, if that's our P, that's our Q, we've got AB over here, then Q is going to be nearest. If it's over here, then P is going to be nearest. If we're somewhere in this in-between ground, then we've got some nearest point on the line between P and Q, and we showed in part 4 that there is just 1 point. That is what it is. Just wondering how part 5 just doesn't seem to have anything to do with anything in this. It was a bit of a weird one to just sneak in there, because part 6 seems to be following on from part 4, not on from part 5. But that last part wasn't so bad. That's a mixed bag of a question. The first part was fine. The second part was really quite difficult. The third part was fine. Fourth part was, yeah, I mean, that was a bit crank to handle. Part 5, I suppose it was a bit of a curveball. It was easy if you could see what they were getting at, but they're trying to muddle things by keeping, talking about this AB all the time, whereas really we're just trying to define the points in S and the relationship between each of the coordinates. And then part 6 follows on quite nicely from what we've done before. So yeah, not a bad question. It was a bit of a mixed bunch. I do like part 2 though. That was certainly something to think about, that was different to what you might normally expect from considering these subsets of coordinates and such like. So yeah, not a bad question really.